Hi everyone, welcome to this episode of Keipert Labs. In this video we're going to go through some worked examples of some titration calculations that come up in the booklet that you have. Okay, so the first question that we're going to go through is question 28 on page 28 of the booklet. Okay, so we're told that you've got a solution of sodium carbonate that's made up by referring to 1.314 grams of sodium carbonate made up to 250 mils. So the first part of answering this question is that it asks you to write a balanced equation for this titration. So we're told that we're reacting a sample of sodium carbonate, in which this is the formula for sodium carbonate, is being reacted with hydrochloric acid. So when we have an acid plus a carbonate, we get a salt, so sodium and chloride, plus carbon dioxide and water. But then we can recognize here that we've got two sodiums here and one chlorine here and one of each of them over here, but that won't work. We need to have an equal number of these two, so we need to have a 2 here. That also balances out our hydrogens, and we need a 2 here. Okay, so now we're asked to calculate the concentration of the hydrochloric acid solution. Okay, so our mass of sodium carbonate, we're told, is 1.314 grams and made up in a solution with 250 mils of water. So what we need to do is we need to work out the moles of sodium carbonate first, to work out what's the concentration of this solution. So that many grams times 1 mole for 2 times 22.99 plus 12.01 plus 3 times 16 grams. Okay, the molar mass of sodium carbonate. Okay, and so if we do that, and so we get 0.01239 ... moles. Okay, and so our concentration of sodium carbonate, so using the shorthand with the square brackets, is this number of moles divided by our volume of 250 mils, expressed in litres, and so we get a value of approximately that. Okay, so that's our concentration of our sodium carbonate solution. But then what we need to do is we're saying, all right, well, that's what we're starting with. We need to know, all right, well, how many moles of sodium carbonate is participating in our reaction? Because this is our known. Okay, so we start with our known. We've got a concentration of our known. We're told that we've got a volume of our known that's involved in the titration is 0.02345 litres. Okay, because we're told that that's the volume of that substance that was involved in the reaction. So our moles is equal to our concentration, 0.04959. You'd keep the decimal places in your calculator. Moles for every 1 litre multiplied by this volume. Okay, so that gives us a value of roughly 0.00116 moles. But then when we look at our equation up the top here, that we recognize that for every 1 mole of sodium carbonate that reacts, we need to react it with twice as much hydrochloric acid. So, therefore, our moles of HCl is double that. Okay, and so we get 0.00232 moles of HCl that's involved. Okay, I'm going to shift it up here. Okay, so then our concentration of HCl is our moles divided by volume. So that value, saying, all right, we had that many moles and we had a volume of 25 mils. And so then we crunch those numbers and we get 0.09303 moles for every 1 litre as our concentration. Or we can just moles per litre up there. Keep things a little bit neater. Okay, and that's how we would do that particular question. Alright, let's go through another one now. Okay, so the second example we're going to do in this video is question 30 on page 32 of the booklet. Okay, so I'm just going to flick across to show you the question here. So there's two aspects to this question that we've got. Okay, so we're looking at analysing aspirin tablets for quality control. Okay, so the first stage involves standardization of a sodium hydroxide solution. Remember that sodium hydroxide solutions absorb a lot of carbon dioxide from the air, and so that's going to change its concentration from day to day, or from kind of time to time. So the way that we get around it is, rather than just chucking the solution out, is that we determine its concentration at that moment that we're going to use it to test something else. So that's what this part A is all about, calculating the molarity of the sodium hydroxide solution. So let's do that. Okay, so that we've told that we've got a concentration of we've got a sample of HCl, which is 1.034 moles per litre in concentration. Okay, and so what we're told is that we have a volume of HCl of 25 mils. So it's 0.02500 litres. So our moles of HCl, therefore, then 0.1034 moles for every 1 litre multiplied by our volume, N equals C times V, and so we get 0.002585 moles, which is the same as our moles of our sodium hydroxide, because our equation that we have here, I should have written it up at the top to start with, looks like this. Very simple. Okay, so we've got a 1-to-1 mole ratio, so therefore it's equal to the number of moles of sodium hydroxide as well. Okay, so therefore our concentration of sodium hydroxide, using our bracket notation, is our moles divided by our volume, which we're told was 25.75 mils. So crunching those numbers, doing that calculation, we get a value of 0.1004 moles per litre for the first section. Okay, so that's our 2-mark calculation there. Okay, so in all likelihood, I would imagine that it'd be 1 mark involved in the moles, determining the moles, and then 1 mark for then converting that into a concentration. So let's look at the next bit. Okay, so looking at this, now that we've standardized our sodium hydroxide solution, we are reacting it with aspirin tablets, looking at 3 tablets. Okay, so this is the equation that's provided for you. You can see that it's a 1-to-1 ratio of our aspirin and our sodium hydroxide. And so then we've got 3 tablets were then measured. We then have to calculate the average mass in milligrams of aspirin per tablet. Okay, so looking at the values that we've got here, we can determine the average titration volume. Now, if you look at the numbers, you can also see you don't actually need to do any calculations here, but it's certainly, if you're not sure, it's best to do it. But you can see that we have that we've got one value, like we've got 3 values that are all 0.05 mils apart. So we take the high and then the low and then the middle, and so then the middle ends up being our average. Okay, but by all means calculate that for sure. Okay, so we'll flick back across to the whiteboard to work out the solution to this one. Okay, so we've got a volume of sodium hydroxide of 0.1655 litres, and we've told, we worked out in our first step that the concentration is 0.1004 moles per litre. Okay, so what we need to do now is to use that to work out our number of moles. Okay, so our volume times by our concentration, moles for every 1 litre. So the value that we get is 0.00166 moles, which is equal to the moles of our aspirin. Okay, because you remember that we're seeing that we've got a 1-to-1 ratio in our equation. So however many moles of this that we have is the same number of moles of that react. Okay, so now what we want to do is we want to convert that to a mass of aspirin. So we've got the molecular formula of aspirin up here. So now we can convert this into a mass by multiplying by its molar mass. So 9 times 12.01 plus 8 times 1.008 plus 4 times 16 grams for every 1 mole. Okay, so we get a mass of about 0.2993 something grams. Now remembering that what our question needs to be answered in, that we need to express it in milligrams. So we need to multiply by 1,000. So we're going to go with 299 milligrams. Okay, and so then that's the answer to that part of the question. Okay, so we've gone through two kind of work titration examples. Obviously there is that last little part to this question that's not actually titration related, about the necessity for ethanol. I'll just answer it while we're here. Is that we need the ethanol to help dissolve the aspirin. Aspirin doesn't dissolve overly well in water, whereas the ethanol, because of its intermediate kind of, it's got polar and non-polar parts, it can help to dissolve, kind of bridge between the aspirin and the water to help make it dissolve better, to be measured. Okay, because in a titration, if the parts haven't dissolved, then they can't really be tested by the reaction, because they might just be stuck inside some solid substance. Okay, so we've just gone through two worked examples here, kind of showing you how we set up with an equation that we determine the moles of our known, we translate that into the moles of our unknown, and then we determine, in the first example, we determined the concentration of our unknown. Here we've determined the mass of our unknown, because that's what our question was requiring of us. And so you can see the steps that we've kind of followed. Alright, it's over to you now to keep going with some of those examples. Good luck. Thanks very much for watching. Bye for now.